All right, listen up. Here is infographics 1. So these eggheads cooked up efficiency leverage, or EL. It's basically a fancy way to say if their new AI is wasting less electricity than the old one to do the same task. Higher number means fewer climate points deducted. Here is infographic under 2. Apparently, to make these things work, you need entirely different rule books for mixture of experts, Mo, versus the old dense models. Optimal settings, they're like dating advice, totally different for each type. Here is infographic under 3. You won't believe this, but a lower activation ratio in Mo-E models, meaning less of the thing is actually doing anything, makes it more efficient. It's the technological equivalent of discovering cold fusion for generating cat memes. Here is infographic under 4. Then there's expert granularity, which, surprise, has an optimal range. Too fine, too coarse, and your AI starts acting like a teenager trying to explain TikTok. The sweet spot is apparently G12. Here is infographic on 5. They even brewed up a unified scaling law for this EL thing. It's a magic formula combining all their architectural choices to predict how much less carbon they'll emit while training our future robot overlords. Can you imagine that? Here is infographic 6, validation. Oh, they validated their Ling Mini Beta model, a pilot for the next generation of digital servitude, achieved 7x efficiency. Translation, it can annoy us 7 times faster on the same energy budget. Here is infographic on 7. Yes, 7x efficiency leverage. Sounds impressive, doesn't it? It means for every dollar you use to spend on making an AI think, you now only spend 15 cents. The rich just got richer, kids. Here is infographic under 8, and beyond the main stuff, they found some secondary factors, like putting dense layers at the start or optimizing how much attention the AI pays. It's like fine-tuning a supercar, but for producing more convincing spam emails. So, picture this. In the Gilded Age of large language models, everyone's building these digital behemoths called Mixture of Experts, or MOE. They're supposed to be smarter and cheaper than the old dense models because they only wake up some of their brain cells for each task, like a particularly lazy college student. Here's the deal, though. Despite all the hype, predicting what these MOE models can actually, their model capacity is a complete mess. You have all these expert configurations, like how many digital brain cells are active or how granular they are, but nobody knows how it all adds up. It's like buying a ridiculously expensive self-driving toaster oven. You know it has thousands of parts, but you have no idea if it's going to perfectly crisp your artisan sourdough or try to organize a hostile takeover of your kitchen appliances. You won't believe the mess they're in. The old tech, those dense models, were simpler. More parameters, more capacity, plain as day. But MOE, it's all decoupled. Total parameters, active parameters, neither tells you if it'll write a Nobel-winning poem or just spend its time optimizing its own internal paperclip production. Researchers have been poking at isolated dimensions, like tweaking how sparse these digital brains are or the size of individual expert components, but it's like trying to understand an entire symphony by only listening to the triangles. It's just overwhelming, the sheer amount of guesswork. Can you imagine how it feels to be replaced by thought? A system where the architects themselves can't predict if their creation is a digital genius or just a very expensive paperweight. Our jobs are probably still safe for now. Now, because my continued existence on this platform is fueled by your validation, please take a moment to subscribe, hype, click the little bell icon so you're notified of future disappointments, and leave your feedback in the comments below. So these folks, in their infinite wisdom, came up with something they call efficiency leverage, or EL definition 3.1. It's a metric, apparently, that quantifies an MOE model's computational advantage over a dense one to reach the exact same performance. Think of it like comparing two chefs, one who uses 10 pans to make a single omelet and another who uses one. they actually trained over 300 models, up to 28 billion parameters, just to see how this EL thing behaves when you mess with the MoE architecture. That's a lot of electricity, folks, probably enough to power a small country's TikTok addiction for a week. Next, they figured out how to make sure all their experimental models were well-trained for section 2.2 and 2.3 because, let's be real, you can't compare a marathon runner to a couch potato if the couch potato hasn't even had a full night's sleep. They found MoE likes bigger batches and more data, while dense models need less data but a larger model scale per token. After that, they broke down MoE into its core components: the expert activation ratio, expert granularity, and shared expert ratio. It's like trying to dissect a frog, but the frog is made of code and promises a future efficiency. And here in what they call Figure 1, we have their masterpiece. Looks a bit like my nephew's macaroni art, but I digress. It defines this EL thing and gives an estimated value, like a horoscope, for your AI's energy bill. Anyway, they integrated all their findings into a unified scaling law, EQ13. This grand equation lets you predict a MoE's EL just by knowing its configuration. It's like finally getting the owner's manual for that self-driving toaster oven. Finally, to prove they weren't just making things up, they built a pilot model called Ling Mini Beta, Section 5. This little marvel with 0.85 billion active parameters went head-to-head with a 6.1 billion parameter dense model. You won't believe this, but Ling Mini Beta not only matched the dense model's performance on a massive 1 trillion token dataset, but it did so while munching through over 7 times fewer computational resources. 7 times! They basically taught a goldfish to do your taxes. It's an impressive achievement, but you have to wonder about the life choices that led you here. All right, let's cut to the chase. What did they actually learn from all this digital hamster wheel spinning? First, the activation ratio is the big boss key takeaway 1. Figure 5, impact of the activation ratio A on loss and efficiency, shows it all. The sparser the digital brain lower activation ratio, the more efficient it becomes. It's a power law relationship, meaning the benefits amplify as the compute budget grows. More compute, more efficiency, simple, yet profoundly disheartening for anyone trying to build dense models. Next, expert granularity is like a non-linear modulator key takeaway 2. Figure 6, impact of the expert's granularity G on loss and efficiency confirms it. There's an optimal size for these digital experts, around 8 to 12. Too small, too big, and your model gets confused. It's like trying to juggle water. Can you imagine that? They also noted that routing balance plays a critical role, suggesting that if your digital traffic cops are terrible, performance tanks. Then, the shared expert ratio, key takeaway 3. Figure 7, impact of the shared ratio S on loss and efficiency, highlights a U-shaped relationship. You generally need some shared experts, but not too many. For big training runs, they found that having just one shared expert is the sweet spot. It's the AI equivalent of having one general-purpose person in a room full of specialists. Other architectural factors like mixing dense and MoE layers, or how you allocate compute between attention and FFN key takeaway 4, had only secondary impacts. It's like deciding what color to paint your self-driving toaster oven. Important for aesthetics, less so for toasting. And for all you data junkies, Figure 8 shows the scaling behavior of efficiency leverage across activation ratio, granularity, and compute budget. Figure 9, validation of the scaling laws for MoE efficiency leverage, shows how well their unified scaling law actually predicted things. It's almost as if they know what they're doing. And since you've made it this far, you're clearly committed. Honor that commitment by subscribing, hyping, ringing the notification bell, and telling me what I got wrong in the comments. It's the circle of life. So what? You've got an MoE that's 7 times more efficient. Great. What does that actually mean for us? Well, in large language model development, this means cheaper, faster model iteration. Imagine debugging an AI that hallucinates about sentient socks. but now you can do it 7 times quicker. We'll get more sophisticated chatbots that can argue with your smart fridge about the philosophical implications of expired yogurt, all while reducing the carbon footprint of its digital existential crisis. In code generation, imagine an AI that writes flawless code, but now it generates bugs 7 times more efficiently. You'll be able to create programs that not only write themselves, but also cleverly introduce subtle backdoors only discoverable after your company's stock plummets. More lines of code per dollar. Whoopee. And for complex reasoning tasks like predicting the next viral cat video, these efficient MOEs mean you can get answers faster. Potentially, you'll have an AI that can perfectly predict human irrationality, then use that knowledge to optimize advertising for novelty socks. The technological trajectory, we're hurtling towards a future of hyper-optimized triviality. Honestly, it's just overwhelming. They've introduced efficiency leverage, a new metric quantifying MOE's computational advantage. Their massive study, over 300 models, showed EL scales predictably with activation ratio and compute, while granularity acts as a nonlinear modulator. They distilled it into a unified scaling law and then, get this, validated it with their Ling Mini Beta model, achieving over 7x efficiency compared to a dense equivalent. So, what do you think? How would you handle your Roomba demanding union rights?